Okay, today is the 19th of April, 2026, and we're doing problem of the day. Alright, maximum distance between pairs, between a pair of values, more maximum distance. You are given two non-increasing, meaning doesn't ever go up. Okay, you're given two non-increasing zero-indexed integers, arrays num1s and nums what? Nums1 and nums2. You're given two non-increasing zero-indexed integer arrays. You're given two arrays non-increasing nums1 and nums2. Okay, a pair of indices ij, where I is a valid index and j is a valid index for nums1 and nums2, is valid if both I is smaller than or equal to j. So I is like, okay, I is smaller than or equal to, and nums1 of I is less than or equal to nums2 of j. The distance is therefore j minus I. Okay, so j has to be bigger than or equal to I, and nums2 at j should be bigger than or equal to nums1 at I. Valid index, okay. Return the maximum distance of any valid pair. If there are no valid pairs, return 0. And non-increasing means, yeah, the previous number is equal to or bigger than the next number, the current number, for every thing in the index, for every valid index. Okay. So let's just write down the title. So 1855. This is POTD. Fantastic. Okay, so non-increasing means if I have a particular array, and I read it from left to right, I expect the numbers to decrease. Stay the same or decrease. And just something to note, if I read it from right to left, that means I expect the numbers to increase. Stay the same or increase. That's something that I always sort of draw out. So if I take an example, nums1 looks like 55, 30, was it 5? 5, 4, 2. 5, 4, 2. And nums2 is equal to 120, 10, 10. 120, 10, 10. So yeah, numbers can stay the same as you read across, but they shouldn't go up. And 5. Whoa. Okay. Let me just look at constraints real quick. So the values inside are at most 10 to the 5, and they're all positive, and the lengths are 10 to the 5, and they're not necessarily the same length. Nums1 and nums2 are not increasing, yeah. Yeah, because like 1, 2, 3, 4, 1, 2, yeah, so the lengths aren't necessarily the same. Okay, so we're looking for the max distance that we can between a pair. So if, for example, the I value is here, if the I value is here, we're looking for the first j value. No, we're looking for the rightmost j value that is the same, that is bigger than or equal to I, but has an array value that's bigger than or equal to the value at I. So we're looking for the thing bigger than 55. So j would have to be here. So the distance for I equals 0 is equal to 0 because j is equal to I is equal to 0. If I is at 1, then I'm looking for, well, there's nothing, right? Because j has to be at least 1, and but the value should be bigger than or equal to 30, which it doesn't exist, so I don't think that works. If I is 2, then j can be 2, 3, or 4, in which case I want it to be 4. I want to go to the right as I can, so long as the number is big enough, and that is big enough. So distance of I equals 2 is equal to 2, because j can be 4. Cool. If I is at 3, then j can be either 3 or 4. It has to be 4 because j is, yeah, it would be 4 because we want to pick the rightmost number that is big enough, and 5 is bigger than 4. So then the distance of that is 1. And finally, if I is at 2, sorry, if I is at index 4, then j can either be 4 or j can only be 4, but it can't be 4 because, oh no, it can be 4, but the distance of I equaling 4 is 0 because 4 minus 4 gives you 0. So, naively speaking, I guess I could do this n squared time where, like, you know, I starts at this value and then for j from I up to the end, see which number is big enough, find the rightmost value that is big enough to be bigger than or equal to the current value. But here's my thinking, right? I starts at 0, as you'd expect. You know, my max distance. Oh, I should say that the answer you get is the biggest one of these, so you should pick this one. So distance should be 2. Yeah. Okay. Anyway, moving on. So, I already forgot what I was saying. So, if we start with I equals 0, and we let v0 equal nums1 at 0, my thinking is basically, let's find the first value, starting from the left of nums2, let's find the first value that is too small for 55. So, you know, j starts at 0, and then that's bigger than 55, so that's fine. And then we move on to 20, which is now too small. I'll do this in red, which is too small, right? 55 is over here, j is pointing to 20. So we know that j minus 1, if this is my j minus 1 is the kind of rightmost number that's bigger than or equal to 55. So find j where such that j nums2 at j is smaller than v0 and nums2 at j minus 1 is bigger than v0, bigger than or equal to v0. Now there is the case of what happens if this number is already too small. Then I'm not sure what to do, but for now, let's just leave it like that. So we know that, okay, j being here and j minus 1 being here, we know that the max distance, the distance for I equals 0 would be that j minus 1 value minus I. So it's a bit confusing because we would normally say j minus I, but j, remember, is pointing to the number just to the right of the number we want. J is pointing there, so j minus 1 is the number that is the value. So 0 minus 0 gives us 0, as expected. Then we move I down. And, well, we could sort of start again at 0, but we know that j should be at least 1. And in fact, we know that, I guess, j minus 1 will be big enough for 30 because j minus 1 was big enough for 55. And, like, the numbers are only getting smaller as we go to the right. So if j minus 1 was big enough for 55, then j minus 1 is going to be big enough for 30. So we can kind of keep j in the same place. And we kind of do a similar thing. Keeping j, initializing j to where it was, let's ask the question, how far to the right can we go before we find a number that's too small? And in fact, j is already too small. So we would do j minus 1 minus I. So for I equals 1, v1 equals nums 1. Yeah. And then find j such that, again, nums2 at j is less than v1, and nums2 at j minus 1 is greater than or equal to v1. Now, the distance of I equals 1 is going to be j minus 1 minus I. Now, in this case, though, j minus 1 is at 0, which is bad, right? Because we want j minus 1. We want this index for the valid number to be pointing to at least the same thing as 1, right? Bigger than or equal to 1. So I think I have to do like a max thing. It has to be the maximum between this or 0, because this will be negative. We'll do 0 minus 1 to give us negative 1. So if we max it with 0, then it should be good. And maybe I should do that over here as well, because in the case where, I don't know. Yeah, I have to be really careful, because in the case where, like, let's say you have 55 for nums1 and then like 20 for nums2, 55 isn't going to have any valid pair because the number's only going to get smaller. So I guess what I'm really doing is I have to look for the first number that like doesn't exceed nums at 0. So, you know, I said start at I equals 0, but really I'm starting at the first I value where the array value isn't bigger than nums2 at 0. So food for thought. Anyway, so if I do that for all I, then am I done? And then basically the max distance can be found by taking the maximum between the distance value we just calculated and the currently stored max distance. Would be my expectation. So in terms of setup, my thinking would be start I at 0, start j also at 0. While nums2 at 0, hang on, get rid of this. While nums2 at 0 is strictly smaller than nums1 at I, I write the other hand. While nums1 at I is too big for nums2 at 0, we know for sure that nums1 at I is not going to have any valid pair because it's too big. There's no nums2 at j that's gonna be big enough for nums1 at I. Because nums2 at 0 is the biggest thing in nums2 because it's non-decreasing. So in that sense, I think I can increment I. Now, if I ends up equaling the length, I should say, yeah, while I is a valid index, while I is less than the length of nums1, and this, if I ends up equaling the length of nums1, then I believe what that means is there's no valid pairs. Like, you went through that whole thing, and all the values were bigger than nums at 0, which means all the values of nums1 aren't gonna form a valid pair. So I think that's like early return. Anyway, now at this point, I should be pointing to the first number in nums1 that is smaller than or equal to nums2. So I think then we can start to apply this kind of logic. For I in range, okay. Maybe I shouldn't call it I initially. Oh, that's annoying. Let's call it it's fine. While I is less than the length of nums1. So while it's a valid index, I guess I can make j equal to I initially, right? What am I trying to do? If nums num1, no, yes, if one num1's at I is greater than nums2 at I, then I think you can just increment and move on, right? What I'm saying is like, if nums1 at I, like over here, for example, no, not over here, over, oh, okay, I need to make a new example. If nums1 at like, if nums1 equals like, 2 and then like 1, and then nums2 equals like 3 then 0, the 0 part can sort of have a 0 over here, right? Like this is a valid pair. Obviously the distance is 0, so it's not that effective, but maybe I should change the example. 3, 2, 0, and then this is 2, 2, 2, 2, 1, I think is fine. So like, nums over here, this forms a valid pair. So the distance is 1, right? Here, this forms a valid pair, distance of 0. Here, this I value over here, I equals 2, has no way of forming a valid pair. So there's no point in doing any computation because the first, I guess, candidate is already too small. So any guy to the right is also going to be too small. So that's what this is. That's what that's saying. I equals I increment, move on, and continue. Otherwise, while nums1 at j. Oh, wait. What if I is greater than or equal to the length of nums2? Because the sizes aren't the same. So this could be an invalid index for I. It's a valid index for nums. Sorry, I said this wrong. I could be an invalid index for nums2. It will definitely be a valid index for nums1, but it might not be a valid index for nums2. So I should check that. While nums1 at I, that's like the v value, is greater than or equal to the nums2 at j, j increases. If I have to check, yeah, while j is a valid index, and this is the case, if j ends up equaling the length of nums2, that indicates that up until the very last moment of nums2, nums2 was always bigger than nums1. So in that case, I think the distance calculated is just the length of nums2 minus 1, which is that very last value, that last index, minus the value of I. Yes. Else, I think the distance calculated is the maximum between 0 versus j minus 1 minus I. Like, when this while loop terminates, j will be pointing to the very first value, well, either will be pointing to outside the array, but otherwise it will be pointing to the very first value that is smaller than nums1 and I. That's where j will be pointing. So the value right before it, j minus 1, will be pointing to the value that's equal to or bigger than nums and I. And again, maxing it with 0 is just in case if the j value is pointing to before I. And I'm hoping that that's good enough. And I should have a dist. And then, whoops, and then max dist is equal to the maximum between the current dist value and the stored max dist value. And I will say max dist is equal to 0 or something. I hope this works. And then return max dist. I spelled that wrong. AMX. Very good. Okay. Let's simulate a little bit. Let me think of a new example. I think the given example that I used was a bit strange. 25, 20 is interesting. That's a good edge case, but this is kind of similar to what I had anyway. All right, let's make nums1 equal to like, so non-decreasing means, 8, and then another 8, 7, 3, 2, 1. And then let's make nums2 equal to, so let's make like one value too small, 7, and then another 7. And then like 4, 3, and I'll make this one smaller than nums1, just to try and keep the algorithm on its toes. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4. So I'm hoping there is a max distance. Yeah, so this will be a max distance of 1. Yeah, so I should get a max distance of 1, I think. So let's see. So first things first, I will point to 0. I'll move this down a little bit, actually. So yeah, I will start at 0. And first things first, before we do anything else, we'll make sure that the value we're pointing at is small, no bigger than the first value of this one. Can I actually just say bigger than or equal to I? Because like, surely that's better, right? Yeah. And I is less than the length of nums2. And can I do that? Because like, I don't care about I of 0, like, if I is equal to, I don't care about nums2 of 0 if I is equal to like 2. Like, I'm not going to use these values over here. I'm only going to use this one, If I is equal to length of nums or I is equal to length of nums2, like if you get to the end for one of the indices, that means you never found a valid start. So I think, yeah. Anyway, in this case, I is equal to, so I would go here and we would say, nope, 7 is smaller than 8. Then you go here, again, 7 is smaller than 8, right? So nums1 is too big. Then we get to here and we say, well, 7 over here is equal to 7 over here, so this will call it to determinate. This won't happen. J will start where I is, might as well. No need to start from 0. And what will happen? While I is a valid index for nums1, if I is greater than or equal to nums2, wait, what? Does this make sense? I think this is to say or. If I is an invalid index for nums2 or nums1 I is too big, then move on. I also didn't increment I at the end. Nums1 or nums1 is too big for nums2, then move on. Kind of the similar logic to what happened over here. While j is smaller than the length of, while it's a valid index, j, and nums1 is greater than, nums1 at I is bigger than nums2 at j, move j along. So yes, j at this point is smaller than or equal to nums1, so we're going to move along. And then at this point, j will break out because this won't hold true. Nums1 is no longer, hang on, I did this the wrong way around. this should say less than or equal to. J is less than length of what's the valid index, and yeah, while nums is smaller than or equal to nums of 2. So at this, so it was here, it would say, yeah, that's fine, and then we'll move on to here, and we'll say, hey, hang on, nums 2 is now smaller than nums 1, so we need to break out. Distance is equal to 0, just to make the variable. If j is equal to the length, if j got down to here, that tells us that the previous value was still bigger than the current value of I. So yeah, I think that's fine. Else, distance is equal to j minus 1. That's why we do, so hopefully this illustrates why we do j minus 1. J is pointing to the value that's too small, so j minus 1 is pointing to the value that's just right. So j minus 1 minus I, so 2 minus 2 gives you the 0. So that's the distance for this guy. So I'll do it in black. Distance for I equals 2 is 0. Then we move on. Max distance, of course, will just be 0. Then we move on. J doesn't really need to change, I think. While j is less than the length of nums 2, while it's a valid index, and the number that it's pointing to is bigger than or equal to, move it along, so move along, and then it'll move along again, and it'll break out because this guy will fail. If j is equal to the length of nums, then the distance will be length of nums minus 1, so it's the same j minus 1 idea. Oops, I didn't mean to change the color of it. Length of nums minus 1 over here, minus I. So you get 1. So the thing over here will be 1. Then, if we move I along, if it's an invalid index or the value at the corresponding value over here is too small, it's not. So j, while j is already over here, so that's fine. Distance is 0. If distance is equal to length of num, same thing. So we look at j minus 1, which is over here, 4 minus 4, so you get 0. And then I moves along again. And then at this point, this is where if I is greater than or equal to the length of nums, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So yes, I with equal to 5 is the same as the size of the array, which means I is not a valid index for nums 2, which means there's no way this guy can be have any valid there's no way this guy can have any valid thingy-majiggies, valid pairs. So there we go. And then we pick the maximum and we get 1. So I'm hoping that it generally makes sense. I'll put this example in A87321. And then, what was it? 77743. There are a few other examples, like small cases. Okay, looks pretty good. Let me just try like 3 versus like 1, and then, yeah. I mean, that should just return 0 anyway, right? Cool. So yeah, this is linear because basically I passes through nums 1 once, and then j kind of in portions passes through nums 2 once. So over n plus m or whatever. I think I back it. I don't know where it would go wrong. While I is less than the length of nums 1 and I is, yeah, so we get a good start. We make sure that, that start isn't, because like for example, if you have something like 8, 8, 8, 8, 8, 8, and then you have like 7, 7, 7, 7, 7, 7, then like there's no way to have a valid pair. So we just move on without A. So that's what this will kind of handle. And then while I is a valid index, move along, increment j along until we find that changing point, that breaking point. Go back 1 because that's the best value we can do. And then yeah, okay, I back it. Yippee! Oh, it's on the slower end though. I mean, I'm assuming there's not. I'm assuming it's just like tricks rather than like anything conceptual. Sure. Ij is equal to 0, 0, res is equal to 0. While both are valid indices, if I is, okay, we don't care about that. If nums at j, nums2 at j is greater than or equal to nums1 at I, then you can increment down, you can increment across, sorry. Otherwise, move them both across. Interesting. Okay, if nums2 at j is greater than or equal to nums1 at I, so if it's a valid, like if we found a valid pair, so to speak, then move j along, try again. And if we haven't found a valid pair, if we found the breaking point, I guess, then I should move across, j should move across, and you're doing j minus I. So I was doing j minus 1 minus I. They're doing like... They found the breaking point and then moved j again. I'm kind of surprised by that. Maybe the math like works out. They do res minus 1 as well, which is interesting. So I think what they're doing is like they're taking one more than the valid distance by incrementing j again or something, and incrementing I. Incrementing I and incrementing j, like what you should be doing, quote unquote, in terms of if you're purely looking for the distance, is you should be doing j minus 1 minus I, where I is pointing to, the start of the pair, and j, like we did here, is pointing to one past the point we want, right? So that's the calculation I was doing, and I think it works. What they did was they first incremented I, then they incremented j, and then they subtracted those resulting values, and you get j plus 1 minus I minus 1, which is the same thing as j minus 1 minus I plus 1. So this is what I was doing, and then they have an extra plus 1 term, which is why I think at the end they have a minus 1, just to like offset it, like just to compensate. Okay, fair enough. Definitely looks simpler, so fair enough. I don't know, I kind of liked... I guess it wasn't necessary, but I liked having like a guarantee that we were starting at a valid pair. But I guess this kind of does that for you. So now I'm curious, if I was to just get rid of all this, would it still work? This was more to like organize my brain, but yeah, I guess I don't need it. Yeah, it's about the same. Yeah, I guess I wouldn't... So what's causing it to be that much slower? I mean, he commented out this part, which is kind of like what my thing is doing. Like this is for... Oh no, this is more so to update j so that it... Very intriguing. I think conceptually it's fine. I feel like it's pretty similar. We can go like really far down as well. Well, both are valid indices. I guess I do have a loop in a loop, right? It is still linear for sure, but I guess I didn't have to do that. Anyway, fair enough. I think I don't know. Wow. All right. Fair dues.